The derivatives and integrals of a vector function. So let's start with derivatives. The derivative r prime of a vector function r is pretty much the same as it is for real valued functions. So we're going to say dr over dt is equal to the derivative. So we're going to say r prime of t, which is the limit as h approaches 0 of r prime of t plus h minus r prime minus r of t all over h. So your difference quotient here. We're not going to have to work all that out because we've learned better ways to take derivatives using the power rule, product rule, quotient rule. So the good news is we're going to use these rules and derivatives like we did in Calc 1 because we're still in the components of the vectors are still real numbers. So just as we did before in Calc 1, and like I said, Calc 3 is Calc 1 and Calc 2 in 3 spaces. So this is your difference quotient here over h. You take the limit, and that helps you find your tangent line. So as you can see here, the derivative, r prime of t, is called the tangent vector. Let's make a note of that real quick. So r prime of t is called the tangent vector, just as y prime gives us the slope of the tangent line. So this gives us our tangent vector. And through that, we could find a tangent line parallel to the tangent vector. So we could also come up with the tangent line. Now remember, r prime of t cannot be 0 for that to happen. So we can also come up with the tangent line. That's where we're going with that. And through that, we could find the unit tangent vector. And the unit tangent vector is, as you would imagine, it's the tangent vector in using the unit formula. So that would be the unit tangent vector of t equals r prime of t over the length of r prime of t. So basically, you find your tangent vector, and then you make it a unit vector, and then you have the unit tangent vector. So that makes sense. There's a couple more things we need to see before we get into the fun derivatives and things. So this theorem is helpful. You should write it down. If vector r is f of t, g of t, h of t, which is the same thing as f of t I plus g of t I plus h of t k, where f, g, and h are differentiable functions. Notice they have to be differentiable functions. If they're not all differentiable functions, then you can't do it. Then the derivative of r equals the derivative of each component. So r prime of t equals f prime of t, g prime of t, h prime of t, which could also be written f prime of t I, g prime of t j, plus h prime of t k. And here's the proof if you would like to see it worked out. R prime is the limit, and they're using delta t instead of h in the formula we talked about before, but it's the same thing. Higher mathematics used to use x and delta x, but you can see that we're taking the limit of the quotient of the difference quotient, and then we have the change in t in the bottom, and it comes up with our very pretty derivative. So let's look at the derivatives of some vector functions. The first one says find the derivative of r of t, which is equal to 1 plus t to the third I plus t e to the minus tj plus sine 2t k. Now, you don't have to show a ton of work, but I'm going to do it the long way. So we're going to say, let's let f of t equal 1 plus t to the third. Then the derivative of that is the derivative of 1 is 0, and the derivative of t to the third is 3t squared. Then the second piece, we're going to say g of t equals t e to the minus t. Now that's part of the reason I'm separating these out is to show my work, because I haven't developed a way. I really want you to show your work and it work out. This is the best way I've come up with so far. So if g of t equals this, I'm going to use product rule. So I'm going to take the derivative of t to be 1, and then I have e to the minus t. And then I'm going to keep the t, and the derivative of e to the minus t is e to the minus t. In chain rule, the derivative of negative t is negative 1. So this means my derivative of g of t is e to the minus t plus, actually that's not a plus because we got a minus happening back there, minus t e to the minus t. So that's our second one. We could factor a e to the t out because it's prettier that way. So if we factor out a e to the minus t, we have 1 minus t. That's a pretty derivative. Now let's do h of t. H of t equals sine of 2t. So the derivative h prime of t, the derivative of sine of 2t is cosine of 2t. Chain rule, the derivative of the 2t is 2. So then r prime of t equals, the first derivative is 3t squared, and we're using the ijk notation, plus e to the minus t times 1 minus t times j, plus 2 cosine 2t times k. So that's the derivative. That's part A of the problem. We're going to talk about part B in just a second, but take a second, make sure you understand the derivative. Part B said find the unit tangent vector at the point where t equals 0. So we're going to need our original function and our derivative. So then let's find our unit tangent vector. Now remember that the unit vector, I'm going to write it over here, our unit vector is equal to A over the length of A. And I'm not big on memorizing a whole bunch of formulas, but our tangent vector is equal to r prime over the length of r prime. So it's the same formula, but instead of using the vector A, we're going to use the vector r prime, which makes sense. So we don't need our r after all. In order for you to get all of this, I'm going to go ahead and say the directions say find the unit tangent vector at the point where t equals 0. So that's nice because no one wants to find a unit tangent vector without it. You usually have a value. So we're going to say t equals r prime of 0, the vector, over the length of r prime of 0. So that means we have a vector on the top. And when we fill in 0, we get 0. And then when we put in 0 for j, we end up with e to the 0, which is 1. I'm going to write this out because it works better in my life that way. And 1 minus 0 is still 1, and we have j here, plus 2 cosine of 0, and cosine of 0 is 1, k, and then let's work on the bottom. So we have 0 squared is 0, plus e to the first times 1 is 1, squared is 1, plus 2 times 1 squared is 4. So this means we have 1j plus 2k over the square root of 5. So when we finish this, we end up with 1 over the square root of 5, 1 over the square root of 5j, plus 2 over the square root of 5k. Now, I am perfectly happy with those answers. Your textbook is happy with those answers. WebAssign might need it rationalized. If they do, it's the square root of 5 over 5j, plus 2 square root of 5 over 5k. I don't think WebAssign does. I think if you give it to them unrationalized, it will be fine. All right, let's look at another one. Okay, for this example, it says for the curve r of t equals the square root of ti plus 2 minus tj, find r prime and sketch the position vector r of 1 and the tangent vector r prime of 1. So the first thing we want to do is we have r of t, so let's find r prime of t. So let's take the derivative. The derivative of t, the derivative of the square root of t, remember that's t to the 1/2, is 1/2 t to the minus 1/2 I, plus the derivative of 2 minus t is negative 1j. So let's rewrite that to be the derivative of t is 1 over 2 square root of t minus I minus j. Now remember that this is parametric and x equals the square root of t and y equals 2 minus t. So if you put your TI-84 calculator in parametric mode and go to y equals, you can graph this. And that's the way I'm going to pull mine up. So hold on a minute, let me pull it in for you. So here we have the curve using parametric equations, but we could have found the equation of the curve by eliminating the parameter. So let's come over here, and we know that x equals the square root of t. That's our first given equation here. And then y equals 2 minus t. So let's take this one and solve it for t. If x equals the square root of t, then t equals x squared. So then we know that y equals 2 minus x squared. Now I could easily do a sketch of that because that means I cross the axis at 2 and it's a parabola opening down. So it's going to cross the axis in these areas. So you have two options. You can look at the parametric curve, or you can eliminate the parameter and come up with a nice Cartesian equation. But we're looking at half of this, and it's going to work out for us. So let's run with it there. Now notice it says find r prime. We're starting with t equals 1. Notice that we're supposed to find r prime and sketch the position vector r1 and the tangent vector r prime of 1. So right here we have our tangent vector. Let's find r prime of 1 while we're here. So this is 1/2 I when you put in 1 for t minus just j. There's no t to plug it in. So we have found the tangent vector here. That's what we were supposed to do at r1. And we're supposed to sketch the position vector at r1. So let's find r1. When we plug that in, the square root of 1 is 1i, plus 2 minus 1 is 1j. So that means we have the point 1, 1 right here. This is the vector r at r1. So this is r1. So the way we sketch our tangent vector is we start at the point 1, 1, which is our corresponding r1 point right here. And we're going to point our tangent vector in the direction of the increasing t. So as t increases, this line goes down, so our tangent vector goes down like this. I'm not going to draw it very long, I'm just going to draw it like that. So we have sketched in our tangent vector r1. This one says find the parametric equations for the tangent line to the helix. Given the parametric equations, x equals 2 cosine t, y equals sine t, and z equals t at a specific point, 0, 1 pi over 2. Good news. No sketching involved. Just find the parametric equations. So let's start with, let's put this into a vector. So r equals 2 cosine t, sine t, and t. And then we know that cosine of t is 2 cosine of t is differentiable, sine of t is differentiable, and t is differentiable. So we can find the derivative r prime of t. So let's do it. R prime of t equals the derivative. I guess we could leave the t off, but we got it here. The derivative of cosine is negative sine. So we have negative 2 sine of t. The derivative of sine of t is cosine of t. And the derivative of t is 1. So here we have our vector equation for the tangent line to the helix. So remember that in order to find, we're supposed to find the parametric equations, which means we need to find the equation of the tangent line. And in order to find that, we need a point and a vector that go together. Now, we kind of have a vector, but the vector has functions in it and not numbers. So we need to find a number. So let's back this up and think about what we've got and what we know. If r equals 2 cosine t, sine t, t, and we have a point, let's call it P, and it's 0. I'm going to spread these out to match. So it's 0, 1, and pi over 2. Then hopefully we could let t equal pi over 2, and that would take us from r to p. So let's plug that in. If we did r of 2 cosine of pi over 2, well, cosine of pi over 2 is 0, times 2 is 0, so that's good. And then we have sine of pi over 2, which is 1, so that's good. And then we have pi over 2, and that's good. So if we let t equal pi over 2, this gives us the point. Now the point of that is if we need to plug that into our derivative, because our derivative gets us to our tangent line. So r prime of pi over 2 is negative 2 sine of pi over 2, cosine of pi over 2, and 1. Now we just did this, so that should help us out a lot. So r prime of t, or pi over 2 specifically in this case, is sine of pi over 2 is 1 times negative 2 is negative 2. Cosine of pi over 2 is 0, and then we have a constant 1 here at the end. And we also have the point 0, 1 pi over 2. So now we should easily be able to find our tangent line. Let's call it, nope, capital T is our normal tangent line. Normally we call our equation line R, so they didn't give us any fancy notation. Let's just call it A. So A equals the vector 0 minus 2t gives me negative 2t. And then we have 1 minus 0 is 1. And pi over 2 plus 1t is t. So that is our tangent line right there. And if we go back to the problem, it asked us for the parametric equations for the tangent line. So our parametric equations are x equals negative 2t, y equals 1, and z equals pi over 2 plus t. So those are our parametric equations. And we're not going to graph this, but there is a pretty graph picture, so I'm going to bring that in real quick. So here's the picture of the helix that we've looked at before, and the red line to the right over here is your tangent line. So it's not too bad to find, not too fun to draw. I'm going to leave this on the screen so we can talk about it a little further, but I'm going to make a note down here and then I'll come back up. So we can have second derivatives. So just as in the normal real valued functions, the second derivative is the derivative of r prime. That's different than our parametric functions, so that's interesting to note that if we take r prime and we take the derivative, we get our second derivative, the second derivative of r. So let's go back up here to this example here. This example here, we have r prime of t equals. So if we keep that, I'm going to do it out here to the side. So if we find the second derivative here, we would say the second derivative of r equals, well, the derivative of negative 2 sine t is negative 2 cosine of t. The derivative of cosine of t is negative sine t. And the derivative of 1 is 0. So that works out really nicely because we take it component-wise, the second derivative of each. All right, let's talk about some differentiation rules. Here we have a theorem that shows us our differentiation rules. And suppose u and v are differentiable vector functions. C is a scalar and f is a real valued function. Then if you're going to take the derivative of a sum, you can take the derivative of both vectors separately and then add them. If you're going to take the derivative of a vector times a scalar, then you can take the derivative of the vector, multiply it by a scalar. If you're taking the derivative of the product of a function and a vector, you're going to use the product rule. So f prime of t times u of t plus f times u prime of t. So you'll see the product rule happening there. One of them is a vector, one of them is a function. In number 4, we have the derivative of the dot product of two vectors. So you're going to take the dot product of u prime times v, and then you're going to add the dot product of u times v prime. So it's the product rule in play here, but there's dot products in the process. Number 5 is the derivative of a cross product. So you're going to take the derivative of the cross product, where one of them, u prime cross product v, plus u times the cross product of v prime. And then the last one, you're taking a composite function, the derivative of the composite function, that's chain rule. See, the derivative of the outside times the derivative of the inside. So you have a vector that contains another function. These all kind of make sense. These number 3 in the middle here, 3, 4, and 5, they're going to be a little interesting to pay attention to. But whether you're multiplying by another function, whether you have the dot product or whether you have the cross product, you still are using derivatives in the product rule. So I don't think it's too terrible. There's a theorem that says that if the length of r of t is equal to a constant, then r prime of t is orthogonal to vector r of t for all of t. Geometrically, this result says that if a curve lies on a sphere with the center at the origin, then the tangent vector is always perpendicular to your position vector. So r prime is always perpendicular to r. And based on the theorem above, remember that the dot products equal 0 if it's orthogonal. So if you have that r prime of t is orthogonal to all r of t, then we know that our dot product with r of t has to equal 0. So that's an interesting result to look at. Let's do 2 examples before we switch to integrals. So the first one, this is just an interesting problem. So we have r of t equals sine squared of at I plus t e to the bt j plus cosine squared of ct k. Now we know that they always make the problems more interesting in your homework than they do anywhere else. So I'd like to be able to send you comfortably into your homework. So let's look at r prime of t. Like I did before, because there are so many steps involved, I'm going to say x equals sine squared at, and let's look at x prime. So the derivative of sine squared of at, remember this can be written as sine of at quantity squared. So that helps you see the chain rule. So we have 2 times sine of at to the first power. Now the second chain rule is we're taking the derivative of sine of at, and the derivative of sine of something is cosine of something. And then the third chain rule, the derivative of the at is a. So x prime really is 2a times sine of at times cosine of at. It's pretty. And then we're going to let y equal t e to the bt. Then y prime, we're going to use product rule. So the derivative of t is 1, and we keep the e to the bt. Plus we keep the t, and the derivative of e to the something is e to the something. Chain rule, the derivative of the power bt is b. So we can rewrite this to be e to the bt plus bt e to the bt. It's kind of interesting. Let's factor out the e to the bt, and we have 1 plus bt. And then let's do z. So if z equals cosine squared of ct, so again, let's write this as cosine of ct quantity squared. So we have 3 chain rules happening here again. So the derivative of z is the parentheses. So we have 2 of the parentheses to the first. And then we're going to take the derivative of cosine of ct, and that's negative sine of ct. And then the derivative of the ct is c. So z prime is 2c cosine of ct. There's a negative sine of ct. So then we can say that r prime of t equals our x 2a sine at cosine at. Our y prime is e to the bt, parentheses 1 plus bt. And our z is negative 2c cosine of ct sine of ct. All right, let's look at one more. This one is similar to one in your homework. It says let r of t equal e to the 2t, e to the minus 5t, and t. You're supposed to find all kinds of things. The first one is r prime of 0. The second one is t of 0. Remember, that's your unit tangent vector. The third one is your second derivative at 0. And then you're also supposed to find r of 0 cross r double prime of 0. All right, so let's start with the first derivative. So r prime of t equals, these aren't too bad, so I'm going to go ahead and do them here. You have e to the derivative of e to the something is e to the something times the something. I'm going to bring it down and clean it up. So the first derivative is 2e to the 2t. The derivative of e to the minus 5t is e to the minus 5t times the minus 5. So we have minus 5e to the minus 5t. And the derivative of t is 1. So here we have a 1. So here's our first derivative, and we're asked to find r prime of 0. E to the 0 is 1 times 2 is 2. e to the 0 is 1 times negative 5 is negative 5, and there is no t, so that value is 1. Now we're asked to find the unit tangent vector at 0. Now remember, this is r prime of 0 over the length of r prime of 0. So that means we have the vector 2, 5, negative 5, 1. Watch me lose that negative. Be careful there. And on the bottom, we're going to do the square root of 4 plus 25 plus 1. So we have 2, negative 5, 1 over the square root of 30, which cannot be simplified. So this means t of 0. Let's go ahead and write it nicely here. T of 0 equals, we have the vector 2 over the square root of 30, negative 5 over the square root of 30, and 1 over the square root of 30. Remember, this is your unit tangent vector, so it's nice and pretty. All right, so let's find our second derivative now. We're up here to the third piece, the second derivative of r. So we're going to go back up to our first derivative and take the derivative again. So I have 2e to the 2t. So I have 2. The derivative of e to the 2t is e to the 2t times 2. And then I have negative 5, e to the minus 5t. The derivative of e to the minus 5t is e to the minus 5t times minus 5. And the derivative of 1 is 0. So our second derivative is, this is not at 0, this is at t. Let's fix that notation here. This is at t. So our second derivative at t is 4e to the 2t, 25e to the minus 5t, and 0. So now we need to find our double prime of 0. So when we plug in 0, and e to the 0 power is 1 times 4 is 4. E to the 0 power is 1 times 25 is 25, and 0. So now we found the second derivative at 0. We have one last real task here. We have the cross product of the first derivative and the second derivative. So let's come down here and we're going to say r prime of 0, cross product r double prime of 0. So we're going to draw our matrix, ijk. Now the first derivative is 2, 5, negative 1. Sorry, 2, negative 5, 1. Let me try to read that correctly. My second derivative is 4, 25, 0. All right, so let's go ahead and do it using the cofactors. And so we have I, and cross off the appropriate rows and columns. So we have negative 5, 1, 25, 0, minus j. Crossing off, we get 2, 1, 4, 0, plus k. And we have 2, negative 5, 4, 25. Now, I don't know if you've seen the other videos, but I need my diagonal lines to keep me straight. And they're helpful for everyone, so it's not a bad thing to get in the habit. It's called build that muscle memory, so you do it well. So here we have 0 and minus 25. Let me switch writing utensils. 0 and minus 25. Changing the signs going up, so we have negative 25i. And here we have 0 minus 4 times a minus j gives me a plus 4j. And 50 and minus a negative 20 gives me plus 40 plus 70k. So we could write this using the same notation we've been using for the whole problem to be negative 25, 4, 70. And that should help set you up to do that problem well. So the next step is to look at integrals. The definite integral of a continuous vector function r can be defined like we did before in Calc 1 or Calc 2 or both, but we can express the integral of vector r in terms of the integrals of the components f, g, and h. So we're going to use similar notation that we used through Calc 1 and Calc 2. So you'll see this notation looks the same. It's based on limits. And the box right here is what I would make note of. The integral from a to b of a vector r of t equals the integral from a to b of f of t I plus the integral of a to b from g of t with respect to tj plus the integral from a to b of h of t with respect to tk. And so we can integrate it by components. So we can evaluate the integral by doing each piece separately. Now we could also say that the integral from a to b of r of t dt, remember it has to be with respect to something, don't leave that off, is equal to some vector r of t, like we use the capital F from a to b. So this means that we can find the vector r of b minus the vector r of a. So we can evaluate it at the definite integral just like we did before. The thing I would say here is what makes it hard is you learned a lot of techniques of integration in Calc 2, and you might see them, you might not. You're going to see at least U sub regularly and possibly integration by parts, but probably integration by parts. But you should go back and brush up on that. They're helpful for differential equations as well, so don't let those out of your brain. So let's look at some of these. The example says if r of t equals 2 cosine of ti plus sine of tj plus 2tk. So there are two parts to this problem. Part A says find the indefinite integral, the integral of r of t with respect to t. And part B says find the definite integral from 0 to pi over 2 of r of t with respect to t. So let's do part A, and we're going to integrate r of t dt. So when we do, we're going to integrate each piece separately. Now I'm going to write it out in painstaking detail on this first one. So we have the integral of 2 cosine of t dt I plus the integral of sine of t dt j plus the integral of 2t dt and k. Now, I don't know that you need to write that out every time. Just know that it's happening. So when we integrate 2 cosine of t, the integration of cosine is sine. So we're going to say 2 sine of t I. And the integration of sine of t is negative cosine of t j. And the integration of 2t is t squared, and 2 divided by 2 is 1. So we have t squared k. And then we have plus some vector c, which is a constant vector, the constant vector of integration. So this is our integral of r of t dt. So now if we were to, when we do part B from 0 to pi over 2, r of t dt, then we're going to have parentheses 2 sine of t I minus cosine of t j plus t squared k, and the bounds are from 0 to pi over 2, just like we did before. So now I'm going to plug these in and say 2 sine of pi over 2. Sine of pi over 2 is 1 I minus cosine of pi over 2. And cosine of pi over 2 is 0 minus or plus pi over 2 squared. So that gives me pi squared over 4k. And then we're going to plug in 0, and sine of 0 is 0 minus cosine of 0 is 1 j plus 0. So this means we have 2i, our j comes from the last one, so plus 1j plus pi squared over 4k. So this is the answer to the definite integral with the given bounds. So your concept of integration doesn't change. You can still use u sub and change of bounds. And if you need to, you could write your three integrals separately. So it makes it a little bit easier to use u sub and these types of things. Let's look at one more of these that may be helpful when you're doing your homework. So this is from the exercises. We know they get a little more difficult, and it says to integrate parentheses t cosine of t squared I plus 1 over t j plus secant squared t k, all with respect to t. Now, when I looked at the exercises, it looks like at most we have some u sub happening, maybe a couple of them. But I didn't see anything majorly difficult. So let's look at this one. This first part, I'm going to make a note because when you look at this one, that's an easy integral, and that's an easy integral. So rather than write the integral 1,000 times, I'm just going to say note, and I'm going to look at the integral of t cosine t squared I with respect to t. Now this is u sub, so let's let u equal t squared. So if we let u equal t squared, then du is 2t dt. Hopefully u sub is a skill that you have. So dt is 1 over 2t du. So we're going to say the integral of t cosine of t squared. And instead of putting t squared, I'm going to go ahead and put u. And we have our I here, so I'm going to throw the I in. And then we have 1 over 2t du to replace dt. Now the t's cancel here, and 1/2 is a constant, so we're going to pull the 1/2 out front. And we have the integral of cosine of u, and let's say dot I du. Now the I is just representing the component there. So let's just leave it and bring it down. So we have 1/2, and when we integrate cosine, then we get sine of u, and here we have I plus some vector c. Now, when we're going to put vector notation on the end. When you do u sub, you need to show some steps of u sub. You need to indicate you're using u sub and show some steps. Don't just do it all in your head. At least let u equal and show some steps along the way. Let's wrap this up before we go back. So we have 1/2 sine, and u is t squared I plus c. Now let's go back to the original problem. And when we look at this first integral here, the first component of the integral, when we integrate t cosine t squared I, we get this blue answer, which is 1/2 sine of t squared I, plus when we integrate 1 over t, we get natural log of the absolute value of t, j, plus when we integrate secant squared, we get tangent of t, k, plus some vector of constants, c. So you can see that it's not too bad to do u sub or integration by parts or anything that you're asked to do. And hopefully this lesson makes sense and you enjoy it. Have a great day.